Today we're going to look at 6.364. This is the third part of these sections. And this is on exponential decay. Does anyone remember from yesterday, what are the kind of exponential functions we studied yesterday? They weren't called exponential decay. They were called exponential... Remember? So what do you call a graph that goes up? Instead of the graph decaying means it goes down, but when it goes up, it's exponential growth. Yep. So up until now, we've been studying graphs that basically look like this. Exponential growth. It curves up very quickly. Okay. Now we're going to look at graphs that curve down very quickly. Okay. That's exponential decay. All right, so reminder, what's the formula that we use to write an exponential equation?
Y equals K times B. A times B to the power of
Power of x. Y equals a times b to the power of x. Yep. So this is like y equals mx plus b. But we use that when we're doing lines. We do this when we're doing curves. So there's no spot on your notes for that because we already did that Monday and Tuesday. All right. What about the A? How do you figure out the A?
That's like the base. When it's like the 0. X equals 0. You go to the y.
Right. When x equals 0, it's the y. So it's what the y value is in the table when the x value is 0. Yep. And how do you figure out the b?
That is the pattern.
And it's the pattern. And what kind of pattern do you have to have for it to be exponential?
Multiplication.
Yep, multiplication, exactly. It's what the y term is multiplied by each time. So let's say I had some numbers like this. 3, 6, 12, 24, 48. Does anybody see, what am I multiplying by each time?
3.
Yeah, no, not multiplying by 3 each time.
2.
2. 3 times 2 is 6. 6 times 2 is 12, and so on. So that's times 2 each time. Okay. What if I had something like this? 120, 60, 30, 15, and I can keep going.
You're dividing by 2.
Yeah, so it's really like dividing by 2 or multiplying by what?
2.
No, it's not multiplying by 2 because that would be getting bigger each time.
Dividing by 2.
Dividing by 2, but that's the same as multiplying by what?
Negative 2.
Nope, if you multiplied by negative 2, it would be like 3, negative 6, 12, negative 24, and so on. So not
Multiplying by 1/2.
right, you're multiplying by 1/2. Okay? And that's kind of how we have to start to think about it. We can't think about it as dividing by 2 because the pattern has to be multiplication. Okay? So it's timesing by 1/2. Which one of these two do you think is an example of exponential growth? The top one or the bottom one? The bottom one? So you think the numbers are growing in the bottom one, getting bigger and bigger? Yeah, the top. Yeah. So the top one, the numbers are growing. The bottom one is an example of exponential decay. Okay, because you're timesing by 1/2 each time. Now, what's going to happen if I keep timesing by 1/2? Timesing by like 0.5. Okay, the next one would be 7.5. If I keep going, what am I going to get close to?
0.
Yeah, this is going to get very close to 0 if I keep timesing by 1/2. But is it ever going to reach 0?
No.
No. No matter how many times you take half of something, there's still going to be a little bit left. Right? It's going to get very, very small. It's going to start to use scientific notation because there's so many zeros. but it's still something left. Okay. All right. So let's take a look at this page. So what we're going to look at now is I'm going to give you guys a table, and I want you to figure out, is it exponential or not? Okay, so remember, you're looking for a pattern with multiply in the y's. What if the pattern is adding in the y's? Like 0, 2, 4, 6, 8, 10. What kind of function would it be if you're adding each time? It would be what? Linear, right. If the pattern is adding a number in the y's, that's linear. Okay. If it's multiplying, that's exponential. So here's your first one. Okay, let's do this one together. Okay, what do the x's go up by each time? 1, yeah. The x's need to always go up by 1. That's how we figure out the pattern. And what about the y's? They're what? Multiplied by a half. So if I do 1 times a half, do I get 3? Anyone think they see the pattern in the y's? Multiplied by what? By 3, yeah. The pattern is times 3. If you're not sure, you could use your calculator. Put in, let's see, we can type this in a fraction, I think. Let's type in fraction. Let's take 1/9, and let's hit times 3. Okay. Did that give me the next number? All right, then let's take that number and do times 3. Did that give me the next one? Yep. And let's do times 3 again. Did I get the last one? Yep. So it is times 3 each time. All right, so let's write a formula. Molly, can you remind me first, what's the pattern? Or what's the formula we're going to plug into?
Y equals A. It's like
So A times.
Oh, B.
Times B, yep. And then one more thing.
And then it's like, isn't it like 2 as the exponent?
Well, we do need an exponent, but we don't put a number until we start looking at something else. But for now, we just put power of x. All right. So Sam, what's A going to be in this case?
1/3.
1/3. That's the y value when x is 0. And Evelyn, what's going to be B?
Don't know.
Right? How do we figure out B?
The pattern.
Yeah, we look at the pattern. What was the pattern in this case?
Times 3.
Times 3. So that's going to be my B. So 1/3 times 3 to the x. And that's your answer for 1A. Okay. Any question on that one? Why wasn't that one linear? What made that one exponential?
The y's go times 3.
Can you say more about it? What do you mean the y's did what?
They were multiplied.
Yes, that's the key. The y's were multiplied. They weren't added to. Yep. All right. Well, that's the question I just asked you. So is this an exponential function? The answer was yes, because the y's are multiplied by 3 each time. That's the reason. So yes, because the y's are multiplied by 3 each time. And then the rule, well, we already did that. 1/3 times 3 to the x. We just did it up above. All right, so let's take a look at 1b. All right, so there's your table. And remember, when you're looking for your pattern, you've got to figure out what you're multiplying by each time. If you see the pattern is dividing by something each time, then you're on the right track, but you need to rethink it as multiplying instead of dividing. Okay, just like when we had the one, instead of saying divide by 2, you got to think of it as times a half. All right, so what do we think about the x's? Do those go up by 1 each time?
Yes.
Yep. Okay, so that's good. Let's look at the pattern in the y's. Does anybody think that they see what you can do to get from 4 to 1? Yeah.
Multiply by 4.
Yes. All right. If you're not sure, we can check it. Let's do 4, and let's do times. And let me put in a fraction of 1/4. Perfect. 4 times 1/4 is 1. Well, let's see what happens if we multiply by 1/4 again. Let's put in a fraction. 1/4. Yep, and we get 1/4. And we can check it. We do times 1/4 again. I think we kind of see the pattern at this point, though. And that gives me 1/16. So yeah, the pattern is times 1/4. All right, so who could tell me, I mean, we've pretty much said it, but can anybody tell me what I would write on those 2 lines?
Yes, because the y is equal to 1/4 each time.
Yes, yep, perfect. So yes, because the y's are multiplied by 1/4 each time. Yep. Perfect. So yes, the y's are multiplied by 1/4 each time. All right, so now the direction said if it is exponential, write the rule. Okay, so we're going to start out with y equals.
1 times 1/4.
And the a value this time is whatever the number is that's below the 0. So 1. Yep, and what else comes after that?
The times 1/4.
Like that?
To the power of x.
Yep, you gotta have that power of s. Yep. And when I check the homework, some of you shorten that. When there is just a 1 here, multiplying by 1, does that change anything? No. So if you put this, that is also okay. It's a shorter way of writing it, only when this number is a 1. Yep. Any question on that? Yep. Yeah. All right, so let's kind of summarize what's going on here. So at the bottom of your guided notes, it says if a table of data represents exponential growth, so you guys need to fill in what's in bold. If a table of data represents exponential growth, what's going to happen to my y values? As I read further and further down in the table,
Multiply. They'll get bigger.
they're going to get bigger, right? They're going to increase. Yep. And the reason they're going to increase is because you're going to be multiplying by a number that's bigger than 1. Anytime you multiply by something bigger than 1, it makes your number bigger. Okay, that's exponential growth. Okay, exponential growth, that was similar to example 1a. Look at the y values. 1/9, 1/3, 1, 3. What would be the next one after 3? 9, and then times that by 3, 27, and then times that by 3. So they're getting bigger and bigger. Now, example 1b, that's an example of decay. So if a table of data represents, you need to fill in exponential decay, what's going to happen to the y values in that case if you read further and further down the table?
Gonna get smaller.
Yeah, they keep getting smaller and smaller, and I showed you it on the calculator. It's up off the screen a little, but what were they getting closer and closer to?
0.
Yeah, they get closer and closer to 0. But will it ever be 0?
No.
No. Because again, if you have any amount of money and you keep taking half of that, you'd never have 0. It would get smaller and smaller and smaller and smaller and smaller and smaller. But technically it would never be 0. It would just get extremely small. All right, so if a table of data represents exponential decay, the values will decrease. Let me draw 2 pictures, and I just want you to tell me which one is exponential growth and which one is exponential decay. Okay, so we got a graph in blue, and then I'm going to draw one other one in red. Which graph there represents exponential growth? The blue one. As you go to the right, it increases, it goes up off the screen. Which one represents decay?
The red.
Yep, the red one represents decay. And if you look at it, as you go further and further to the right, it looks like the red one is getting close to what number?
0.
Yeah, it looks like it's getting very close to 0. It actually never reaches it. It's just because there's only so much pixels on the screen. You can't show it, but it's just getting closer and closer and closer and closer. Yeah. All right. So let's see. I think this is on the back of your guided notes. So on the back, it says for an exponential function to represent exponential growth, the b value that's the one that has the exponent attached to it, has to be a value greater than 1. Greater than 1. Okay, so you want to fill in greater than, actually the than is already written for you. You just have to fill in the greater and the 1. So I'm talking about that number that I just put a box around. If that number is bigger than a 1, you're going to get a graph that looks like that. In my problem, what's the b value? Let me just fix it so it looks like this. What's the b value in the blue one?
2.
2. Is that bigger than 1?
Yes.
That's why it looks like exponential growth. Yeah.
Where is it at?
Oh, yeah, just sign off. All right, how about in the red one? What's the b value in the red one? 0.5. So what happens in this case is in an exponential function, if the b value is between 0 and 1, that's when you're going to get a graph that looks like that. that's called decay. Is 0.5 between 0 and 1?
Yes.
Yes. Yep. So on your guided notes where it says between, and then you've got some blanks to fill in, 0 and 1. And you could see the number as a decimal or a proper fraction. Okay, so what do I mean by a decimal or a proper fraction? Y equals 1 times 0.5 to the x. Okay, you could see it like that. Or, what's 0.5 as a fraction?
1/2.
Yep, 1/2, perfect. Those are the same thing. If I were to type those on the calculator, they're identical. Right? In this case, I used a decimal. In this case, I used a proper fraction. You could see it either way. And if it was a problem on a test, I would accept either answer, a decimal or a fraction. All right, so let's take a look at a few problems. And you don't have to graph anything, you don't have to make a table. All you have to do is look at the problem like this and tell me, is it growth or decay? Let me put up some examples. Okay, so there's examples 2A, 2B, and 2C. So take maybe a minute or so on your own and see if you can tell me which one of these are growth and which ones are decay. Okay, they're not all growth, they're all decay. There's a mixture. Okay, so just write down which ones are which. And if you're wondering, well, why isn't there an A? Like, where's the number that's in front? They're all ones. So you can just think of it as 1. All the A values are 1. That's why they didn't write them. All right. And then when you get it, call me over and I'll take a look and see if you got them right. Okay, so looking at the first one. Well, first of all, looking at all of them. What's the A value in every one of them? 1. Yeah, you're not looking at the A value to determine if it's growth or decay. You're looking at the B value. Okay. So what's the B value in example 2A? 0.54. Okay, 0.54. Is that greater than 1 or is that between 0 and 1?
Between.
Yeah, between 0 and 1. So is the first one exponential growth or exponential decay?
Decay.
Yeah, I saw some people just wrote decay. That's fine. I mean, technically, they said write exponential growth or exponential decay. But that's so exponential decay. All right, example 2B. What's the B value in that one?
3.0221.
3.0221. Okay, is that greater than 1 or between 0 and 1?
It's great.
Yeah, that's a B value that's greater than 1. So is this exponential growth or exponential decay?
Growth.
Yep, so this is exponential growth. And lastly, example 2C, what's the B value there?
0.993.
0.993. Is that greater than 1 or between 0 and 1?
Between.
Yeah, just barely between. So this one is, but it's still between 0 and 1. So it's going to be
Decay.
decay, just barely. If you were to draw one with a decay rate of 0.993, it's going to decay so slow. It's not going to be like a sharp curve at all. Very slow. All right. So, any question on 2A, B, or C? All right. So the next thing we're going to look at is a graph, and we're going to do the graphing exactly the same way we did it Monday and Tuesday. All right, we're going to pick 5 values for x, and then we'll make a table. Does anybody remember what were the 5 values? You don't have to pick them, but I said it'll probably be easy if you pick them. Easier. Yep.
-2, -1, 0, 1, 2.
Right, -2, -1, 0, 1, and 2. Okay. So let's see if we can graph this one. All right, so you don't have it written down, so you copy that first. Y equals 1/2 to the x. And they didn't make a table for us, so we're going to have to make our own table. And you got a little bit of room to the side. You can make a table. So x, y. All right, so we got -2, -1, 0, 1, and 2. All right, if you get stuck with the arithmetic, the easiest thing is just use the calculator. Okay, let's just plug them in. Okay. What's the first x value that I'm going to plug in according to my table?
-2.
-2. So we're going to do 1/2. Okay, that's how I can do a fraction on the calculator. Hit the exponent button, and then plug in -2. Okay. What did I get for a y value? 4. After you do the first couple, you should start to see a pattern in the y's. If you don't see a pattern, then something's wrong. Okay. All right, what's the next x value I need to plug in? -1. So if you're using one of my calculators, you can do something similar to this, where you just bring up the last thing you typed in and just change the one thing that you want to make different. Okay, it just saves me having to type the whole problem in. Hit enter, and what did I get for a y value this time? 2. Okay, the next one we should know, this one. Next is plugging it in the 0. What do you get when you raise something to the 0 power? 1. Now, based on the pattern, 4, 2, 1, anyone think they know what the next number is going to be? 1/2, yep. And how about the next number after that? 1/4. And if we kept going, then it would be 1/8, 1/16. Keep taking half, that's the pattern. All right. So we've got our table. What do we have to do now? Yeah, now we have to graph it. So -2, 4, -1, 2, 0, 1, 1, we're at 1/2, and 2, we're even a little lower than that. Bless you. Now make your curve best you can. I'll make that a different color so it stands out from the axis a little bit. But you can see what's happening. It's coming down, and it's getting closer and closer and closer to that x-axis. All right, is that growth or decay?
Decay.
Yep, that's definitely decay. Any question on that? If you don't want to pick these as your x values, you can pick different ones. The problem is if you pick numbers that are too big, you're going to get way off the graph. Okay. So I would stick with those 5 x values. All right, compare. When you're doing compares with exponential decay, it's exactly the way I taught you Monday and Tuesday with growth. How does the sentence, when you're saying compare, always start? Yep, a little bit more. Vertical stretch.
By the factor of.
By a factor of. You always start with saying those words exactly. Yep. All right, so let's try this one. So example 4, it's y equals 3 times 1/2 to the x. All right, yeah, I'll let you guys try it because we've done ones pretty similar. Okay, see if you can do that one. And then see if you can do the one below it. And remember, that one has a negative. So you have to add something on the end of what you say. Okay. Notice too, what's the b value in every one of these problems? A half, it has to be. I can't ask you to do a compare problem if these aren't all the same. It doesn't work. Okay, so those will always be the same when you do a compare. All right, so take a couple minutes, try that, and then I'll walk around and check in and see how you guys did. All right, so let's take a look at these two. So remember, when you see the words compare, okay, that sentence needs to start out vertical stretch by a factor of. Okay, and when we say that, like vertical stretch by a factor of, that means like, factor means like how many times you're stretching. So like if it's a 5, it's 5 times as much stretch, right? What's this one? Yes, it's a vertical stretch by a factor of 3. So that means if the original graph was like 1 inch tall, the new one is 3 inches tall, stretched 3 times as much. And when you take something and you stretch it, what a stretch does is it causes it to curve up steeper. That's a vertical stretch. It makes it steeper. All right, how about the second one? What do we? What's the first part of what we need to say?
Vertical stretch by a factor. No.
Right. Yeah. Nobody's really been saying that negative at first, which is good. We don't want to say it when we do the vertical stretch. Okay, so we just say vertical stretch by factor of 1/3. Okay, now, just to be clear what that's going to do. If that's your graph and you stretch it by 1/3, that really means you're going to make it 1/3 as tall. So you're really doing something like that, which makes it more gradual, okay, instead of steep. Okay, so that's stretching by a factor of 1/3. And what else do I have to say?
Reflected over x-axis.
Right. And reflect. I think I saw some people, they might have said flip. That's okay too. And reflect over x-axis, but you do have to say x-axis. If you say y-axis, that's wrong. It's not over the y-axis. All right. So any question on that? All right. So we got a couple just ones at the bottom that say practice A, B, and C. Let's look at one of those. Let's do practice A together because this one's quick. Choose the equation that represents exponential decay. So you have y equals 1.2 to the x, and y equals 1/4 to the x. And then I want to know why you picked the one you pick. Okay, so which equation there represents exponential decay? Yeah?
B.
Yep. B? That's correct. Why?
Because 1/4 is less than 1.
Yep, it's less than 1, but it's still bigger than
0.
0. It's got to be between 0 and 1. Yep. So the answer is B, because the number is between 0 and 1. That's why it's B. The number right here, the B value is between 0 and 1. So if b is exponential decay, a is exponential growth. Yep. Because the value right here is bigger than 1. Yep. All right. So now they want a rule. Okay, given that table. What's missing from that table that I normally give you? Yeah, you don't have the 0 in the x column. So you need to figure that out. So it's almost like we need another row above the one that we have. We've got these. 24, 12, 6, 3. You need to figure out the pattern and go back one more row. What would be the number next to 0 if it follows the pattern?
48.
Right, it would be 48. So that's what you needed to figure out first. Right, so now see if you can write a rule, y equals ab to the x, and then I'll come check your answer.
Well, I put myself there.
All right, so what's the equation that we have to use? The same one we're using all week.
Y equals b times, no, a times b over to the power of x.
Okay, so that's the equation that you need to fill in. How do you get your a value?
This is the 0, and when x equals 0, go over to the y.
Right, look at when x equals 0, then go over to the y. So that's 48. And Evelyn, how do I get my b value?
I don't know how to say it, but it's like, so 48 to 24 would be like multiply.
The b value is what you multiply by each time to get to the next y.
Yeah.
So yeah, what did we multiply by to get from 48 to 24? Yeah, multiply by a half. How about to get from 24 to 12? Yep, multiply by a half. It's times a half each time. So your b value is a half. Now, you just need to write the final answer. So what would be my final answer?
Y equals 48 times to the power of x.
Yeah, perfect. 48 times 1/2 to the power of x. That's your answer. All right. So remember, the homework tonight is 6364 part 3, and then tomorrow we'll do 6364 part 4, and we have our test on Friday. Okay, I will also be after school tomorrow in case anybody needs to stop by for extra help.